Hello everybody. In this video I want to give you guys a few little hints about how to do week 13 quiz 2, where we're going to draw molecular orbital diagrams for all of these different molecules. The first thing I want to do is go over a little bit of review here about how we do electron configurations. So here I'm looking at figure 6.29 from our textbook, and we have this table here, and it's kind of confusing when you just look at it, but it actually makes it really easy for us to get the electron configuration of a specific atom. Okay, so let's do an example here. Let's do bromine. So you can see here that we have this string down here for bromine. Okay, and basically if you want the electron configuration for bromine, this is going to be the end of that electron configuration. So it's going to be this, and then immediately preceding that is going to be the bit of electron configuration for the noble gas that is up and immediately to the right of it, so argon here. Okay, so and then immediately before this bit is going to be the electron configuration for neon, and then the electron configuration for helium. So if I wanted the electron configuration for bromine, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Okay. If I wanted to do the same thing for lithium, I would go all the way back over here, and I would go up, and I would just be at helium. So for lithium, it's going to be 1s2, 2s1. All right. And so following through with this table like that, it's really easy for us to get the electron configurations that we're looking for. The next thing we need to do is look at our chapter. And the first choice we need to make is which of the sheets that I gave you to use should we be using. And there's this phenomenon that occurs that we have to consider here with the sigma 2p orbital. It just happens to be that when we are using when we have elements that are lighter than oxygen, that sigma 2p orbital slides up over the 2p pi orbitals. And then it goes down in energy and down in energy and down in energy. And then for all oxygen and all other elements heavier than it, the sigma molecular orbital slides below those 2p pi orbitals. And it's just a phenomenon that just happens to happen for us. So we need to, if we're doing a molecule that is smaller than oxygen, we need to be using one that has this sigma orbital higher up here, i.e. this guy right here. All right. And if we have one that is oxygen or heavier, we're going to need to use the one where this is shifted down, or this guy right here. We kind of have an idea of how that looks here in this diagram. And basically what we're going to try and do here is we're going to try and figure out how the atomic orbitals that these electrons are sitting in combine together into molecular orbitals that are come in a couple of different varieties here. So we have our sigma orbitals, and those sigma orbitals are responsible for single bonds. Okay, and you can see that we use subscripts here to describe what atomic orbital the electrons came from to form this molecular orbital, and we use superscripts to describe how many electrons are in it. Okay, so it's a little bit of a different notation for us that we have to pay attention to here. Sigma orbitals come in two different varieties. So we can have a bonding sigma orbital that's going to cause bonding to happen, or we could have an anti-bonding sigma orbital that's going to prevent bonding from happening. And we're going to indicate that it's an anti-bonding orbital by putting this star right here. That's what that is all about. The next kind of orbitals that we can have are pi orbitals. So pi orbitals are going to contribute to double and triple bonds. Okay, they have the same sort of notation as the sigma orbitals, but you will see that you would list them inside of these parentheses. You would list both of the pi orbitals that you have filled, okay, with a comma in the center, and then you still use a superscript to indicate how many electrons are in there. And they also come in both bonding forms and anti-bonding forms. Now this seems a little complicated, but once you really break it down, it's really not that bad. So I'm going to switch over to my document camera now, and I'm going to show you guys how to do both lithium and bromine cation. Okay, so we'll start by considering the lithium example. We're trying to make lithium dilithium molecule here. And what I like to do is first start off by thinking about what the two atoms are I'm going to combine. So I'm going to combine a lithium with a lithium and what their electron configurations are. Okay. And what's important to realize is that we're only dealing with our valence electrons here. So we're only concerned about the electrons that are in the highest energy levels. So these inner shell electrons, the ones that are in these lower energy here, these aren't going to play into any kind of bonding or anything. They're completely filled, and there's an equal number of bonding and anti-bonding orbitals, so they're just going to all cancel each other out. Even if you did do them, you'd see that they don't contribute to any bonding. So I've written out those electron configurations, and I can see that I have one electron to play with here and one electron to play with here for those. And then I like to put the thing that I'm trying to make in the center, and I feel like that really highlights what this diagram is about. Okay, down this side of the diagram, I have these horizontal lines that are representing the different atomic orbitals that we have. Okay, we actually don't even need this section for this really simple example because there are no p orbitals to consider. And down this side, I have the atomic orbitals for the other atom. And down the center, I have the molecular orbitals that are being made. And we know that we're going to form just as many molecular orbitals as we are atomic orbitals. So that's why there's 1, 2 atomic orbitals here, and then there's 1, 2 molecular orbitals that we're going to make out of it. And all we need to do is take the electrons that we have and start filling in our atomic orbitals. So we have 1 electron for 2s. We'll label this one 2s, and we'll put 1 electron in it. And that's going to be this little hook like this. You can write it facing down or facing up. It doesn't really matter, but I usually see them starting off with them facing down. And then we have our other 2s here. We have 1 electron in there. Then we need to decide how are these going to combine to fill our molecular orbitals. And basically what's happening with this diagram is as we go up, the energy levels are going up. Okay? You'll notice that this bonding sigma orbital that's going to be responsible for single bonding is below in energy these 2 atomic orbitals. That's energy that is released is what goes into the bonding. And this anti-bonding orbital is going to be higher in energy than the atomic orbitals or the bonding orbital. Okay, so as you're filling them, you almost need to think of it like you're filling a glass of water. We're going to start at the bottom and we're going to work our way up. Okay, so we'll put this electron into our molecular orbital, and then we'll put this electron into our molecular orbital. And then at that point, we've ran out of orbitals. So for this simple example, we're done filling out the molecular orbital portion. The only thing that we need to do now is consider what is our electron configuration. And so using our notation, we go to our sigma 2s orbital here. So we are going to indicate that we have a sigma 2s orbital. We'll put that in these parentheses. We'll indicate that it has 2 electrons in it. The next thing we need to do is calculate our bond order. Bond order is like we've been talking about with single, double, triple bonds, but it actually allows for there to be fractions, for there to be half bond orders. And the way we calculate it is it's the number of electrons that are in all of the bonding or molecular orbitals minus the number of electrons that are in all the anti-bonding molecular orbitals. So we have 2 bonding electrons, and we minus 0 anti-bonding orbitals because there's none anywhere else. And then we're going to divide that by 2. And we're dividing by 2 because it takes 2 electrons to form a bond. And we get a bond order of 1 in this case. And it is actually true that if we had a dilithium molecule, it would be connected with a single bond. Okay, now we can take a look at Br2+, where we have a little bit more stuff going on. And this time we can consider that this could be formed from a neutral Br atom and a Br plus atom, a Br cation. All right. Now I wrote out the electron configuration here, but I used this condensed notation. That's really pretty handy, where I just wrote some square brackets and I put argon in here to indicate that this is the electron configuration of argon. And you can see how useful this is, because now we're only considering, we can only see the valence electrons that we really need to be concerned with, and the rest of it is just kind of tidily tucked away into that notation there. And I did the exact same thing over here, but you will note that because I had a cation, I need to remove one of the 4p electrons. It's not there in this case, and it needed to come off of the 4p electrons. You can go back and review the Ausbau principle if you need a refresher about why that's true, but it should have came off of there. Now I filled out the entire thing here, and you can see how we go about doing that. We have our 4s like we did before, our sigma 4s or sigma star 4s, and then here we have, also note that we have the we use the template where the sigma 4p here is below the pi ones, because we have a atom that is heavier than oxygen, right? And we have our 4px, 4py, and 4pz atomic orbitals. I like to break them out into these as separate atomic orbitals to be really clear. There's some great pictures in the textbook where you can see what a p orbital looks like and how they are arranged orthogonal to each other, with one along an x-axis, one along a y-axis, and one along a z-axis. Then they go and they start forming, and we start down here. Remember that all the ones that are lower in energy than our atomic orbitals are going to be bonding orbitals. So we start off with our sigma 4px molecular orbital, 4py pi orbital, or 4pz pi orbital there. Then we get to our anti-bonding pi 4py and anti-bonding pi 4pz. And then finally at the very top we have our sigma anti-bonding 4px molecular orbital. Now we can fill them in, and you guys can see how we're going to do this when we have a few more electrons that we need to fill in. So an important thing to note is that we are not going to consider the 3d10 electrons. We're not those aren't going to play into this. And the reason being is that they're in a lower energy level. They're further down than these guys here, and they're not going to be participating in bonding under typical circumstances. There's a few really exotic cases where they get involved, but in general they're not going to be involved in making these molecular orbitals. So if we come here, we can see that we have 2 4s's here and 2 4s's there, and we will put them in, and we will put them with opposite spins because they cannot have the same spin inside of the orbital. That's an excited state when they have equal spins to each other. So the lower energy state is going to be with opposing spins. And then we can start filling them into our molecular orbitals here. So I can put one here. I can put one from there here. I can put this other one up here. And another one up here. I have all 4 of them filled in. And now we can see that we have a completely filled bonding orbital and we have a completely filled antibonding orbital. So basically this whole block here is not contributing to the bonding because this antibonding orbital is canceling out that bonding orbital. So all our bonding is going to be happening up here. So we need to fill these in. We get 5 electrons here, and we're going to remember that we're going to put 1 electron in each one of these. And then we're going to go back through and pair them off. We do that because it does take additional energy to pair them off and put 2 electrons in the same orbital. They are repelling each other. So the first thing that's going to happen is you're going to put 1 in each orbital, and then at a higher energy state, you'll start pairing them off. Over here, we need to be careful. We need to remember that we only have 4 this time. And now we have those filled out, and we have to pay attention to how many electrons we have all together. So we got 5 plus 4. We got 9 electrons to fill in our molecular orbitals. We start at the lowest energy state here. We fill this one in. We come up to the next highest energy state. We put 1 in each one of these because they are equal energy, as indicated by being equal to with each other horizontally. Then we can fill in the next ones. So that's 6. Then we have 7, 8, and 9. Now we can calculate our bond order. We have 1, 2, 3, 4, 5, 6, 7, 8 electrons in a bonding molecular orbital, and we have 1, 2, 3, 4, 5 electrons in an antibonding orbital. 8 minus 5 is 3 divided by 2. We get 3/2, or a bond order of 1.5. And we can see that the way we're calculating bond order here, it allows for a fractional bond, a 1.5 bond. And in practice, you will see a bond distance between these 2 bromine atoms in reality that is close to 1.5. It's somewhere between a single and a double bond. If we want to do our electron configuration for that bromine molecule, we have our sigma 4s. It's got 2 electrons. We got our sigma 4s star. It has 2 electrons. We have our sigma 4px with 2 electrons. We've got the pi 4py, pi 4pz bonding orbitals with 4 electrons. We've got our 4py, 4py anti-bonding pi orbital and 4pz anti-bonding pi orbital, and in those there are 3 electrons. And that's pretty much it. I hope that this has been helpful to you guys, and as always, feel free to reach out if you have any questions.